Welcome to Dr. Raz, the Baking Chemist. Today's question is all about vanadium and it's part of the amount of substance topic. It's another request from one of my students. Let's see what we can do. So the vanadium in 50 centimeters cubed of a 0.8 mole per decimeter cubed solution of ammonium vanadate reacts with, ammonium vanadate reacts with 506 centimeters cubed of sulfur oxide. Gas measured at 26, so immediately when I'm looking at this kind of information being given, I'm thinking PV equals nRT, PV equals nRT. Okay, so PV equals nRT. So it's obviously that related. And also, as soon as I'm seeing this, and I'm thinking, okay, what can I already do with it? In my head, I'm thinking, well, I've got the concentration, I've got the volume, so I can work out moles, right? And of course, I've got that and that, so I can work out moles of a gas as well. Hence, PV equals nRT. Right, use this information to calculate the oxidation state. Well, that's interesting. Use the information to calculate the oxidation state of the vanadium in the solution after the reduction reaction with sulfur oxide, sulfur 6 oxide. That's sulfur 4 oxide. So reduction, so it's obviously a reduction reaction. Okay, so they've thrown a curveball here. Okay, it's not as simple as just moles. Let's see. Explain your working. The gas constant is okay. Again, there's another indication. This is a PV equals nRT type question, ideal gas equation. It's a 6 marker, so obviously this is a one of those extended response questions. So coherent, relevant, and logically structured questions. So everything has to have to follow through, and it needs to make sense. Otherwise, you're not going to get full marks. Okay, so extended response. So it's like usually 3 stages, isn't it? Yeah. So let's see what happens. All right. So the first thing, if I see this question, the first thing is I will do what I can from the data given. All right. So I can find moles of vanadium, CV over 1,000, and then I can find moles of sulfur 4 oxide using PV equals nRT. So let's do that. Okay. So here we go. So it's moles equals moles of vanadium equals CV over 1,000. So I'm going to put that equation down, which equals concentration is 0.8 molar times by 50 centimeters cubed over 1,000, which equals 4.00 times 10 to the minus 2 moles. So that's the moles of vanadium. Okay. The other moles that I can find, so I found the moles of that. The other moles I can find is sulfur 4 oxide. Okay. Yeah, Roman numerals. So moles of sulfur 4 oxide. Now, formula of that sulfur 4 oxide, okay, is that SO2. And if you don't know how to work out formula from the name, if you've been given Roman numerals, you need to learn that. Okay. So sulfur dioxide. And that of course is the oxidation state, isn't it? No, oxidation state of sulfur in that case. And that of course, so the moles is PV equals nRT, isn't it? So I'm just going to put that down here. So if I PV equals nRT, that's how I remember it, but it's up to you how you want to remember it. And of course if you rearrange it, so N equals PV over RT. And so the pressure is 98 kilo. Now they've given the kilopascals. That's where one of the places, and you'll see other places where people go wrong, students go wrong, but this is one of the places where they go wrong. Yeah, so pressure is not 98 kilopascals, but 98,000 pascals, because it's pascals that's used in this equation, not kilopascals. And the examiners deliberately do that, okay, just to make sure you're aware. So that's pascals, and then times by volume. The volume is 506 centimeters cubed. Okay. But unfortunately, in this equation, PV equals nRT, the volume used is meters cubed, not centimeters cubed, meters cubed. And a simple way of doing that is 506. Just put 10 to the minus 6, and I'll change it to meters cubed. Yeah, from centimeters cubed to meters cubed. Learn how to do this rearranging, converting from one unit to a different unit, especially in a question like that. You'll need to know. And of course that divided by R, so R they've given us 8.31, and then times by T, temperature. Now the temperature they're given is 20 degrees Celsius, and once again the temperature in this equation is not degrees Celsius, it's actually Kelvin. So you need to add 273 to it. So 273 plus 20 is 2829293. And the answer is 2.04 times 10 to the minus 2 moles. So far, okay, I don't know how to approach the rest of the question yet. I could still get these marks, okay. The problems where students go wrong here is units often, okay. They won't convert them properly, so the centimeters cubed, they'll divide them by 1,000 or 10,000, whatever. It's actually a million, yeah, 10 to the 6. So centimeters to meters cubed is a million, okay. So make sure you know how to convert it, okay, from one unit to another. Right, let's move on. So I've got the moles of vanadium, I've got the moles of sulfur dioxide. I'm coming back to the question now. Calculate the oxidation state of vanadium in solution. Okay, well, if I'm talking about the oxidation state of vanadium, that means that I need, that I might as well find the oxidation state as it is. Yeah, so what is the oxidation state in that ammonium vanadate as it is before the reaction? Because obviously I'll need to know about it afterwards, so I might as well work it out. Now, if you don't know how to work out the oxidation states, I think in one of my previous videos I have actually shown you how to work out oxidation states. So ammonium vanadate. Yeah, so it's as simple as, okay, well, I know what nitrogen is, I know what hydrogen is. So nitrogen is -3. All right. Hydrogen is +1, but there's 4 of them, so +4. Vanadium, I'm trying to work out X, and then oxygen -2, that's times 3 is -6, so it's -3 plus 4 plus -6 equals, +6 equal plus X equals 0. Okay, and then of course X equals, so I'm going to bring that across, +3 -4. Could have done added it all together here, but never mind. -6. Okay, so +3 -4 plus 6, so that's 6, 7, 8, 9. 9 minus 4 is +5, so it's +5. So the oxidation state of vanadium is +5. Okay, we will need to know that later, but let's see. Right. And then they're saying using after the reduction. Okay, so now after the reduction with sulfur 4 oxide. Now what we need to know is that when sulfur dioxide acts as a reducing agent, it gets oxidized. And going back to our oil rig terminology, oxidized, so this sulfur gets oxidized, that means it loses electrons. The question is, how many electrons does it lose? Well, it becomes, well, it is oxidized, sulfur gets oxidized from 4 plus 4 as it is over there to +6. Okay, so here as it is there, you can work it out, the oxidation state of sulfur is +4. Now whenever sulfur is oxidized, so in other words when it's acting as a reducing agent, it becomes a sulfur +6 oxidation state. Okay, so in other words, each time, each sulfur, when it acts as a reducing agent, okay, it loses 2 electrons from 4 to 6. Yeah, so it's lost 2 electrons. Okay, so sulfur dioxide, we've got to say sulfur dioxide lost 2 electrons. And that's each mole. So each mole of sulfur has lost 2 electrons. Okay, and I should probably put it in proper sort of English. Remember, it needs to be coherent, yeah, and logical. So each mole of sulfur loses 2 electrons. Okay, so the question is, how many moles? Now, if you go back to this, how many moles of sulfur dioxide did I have? Well, I had 2.04 times 10 to the -2 moles. So I had 2 points. So that means how many moles of electrons is lost. So if I had, so moles of electrons lost by sulfur, okay, or given, is equal to 2.04 times -2 times by 2, because each mole of sulfur dioxide loses 2 electrons. So each mole of sulfur, remember I'm talking about sulfur dioxide because that's the molecule, but it's the sulfur that's losing the electrons. So each mole of sulfur has lost 2 electrons. Okay, so the total number of moles of electrons lost is 4.08 times 10 to the minus 2. Okay, so that's the number of moles of electrons lost. Now remember, look, these kind of annotations are important, yeah, because remember, this is one of those extended questions, so you have to make it clear. Right, so let's move on. So that's the number of moles of electrons lost. Or, you know, lost by sulfur, but given to what? Given to the vanadium. Okay, given to vanadium. So now, remember what I said earlier? I'd worked out the oxidation state of vanadium to be +5. Well, the total moles of electrons now that this vanadium has received is that many moles. But how many moles of vanadium did I have in the first place? The moles of vanadium that I had in the first place, going back to right back to our first question, I had 4.00 times 10 to the minus 2 moles of vanadium. Okay, so how many electrons does each mole of vanadium take? So that's what I've got to work out. So electrons per mole. So electrons per mole of vanadium. Okay, so moles of electrons per mole of vanadium. Okay, so how many moles of electrons has each mole of vanadium taken? Okay, and that's what I'm trying to work out here. So all I'm saying is, well, vanadiums, how many moles were there? 4 times 10 to the minus 2. Electrons, how many moles were received by vanadium? 4.08 times 10 to the minus 2. So 1 mole of vanadium has gained divided by 10 to the minus 2. And the answer there is approximately 1 mole. So you can work it out. You'll notice it's very, very close to 1. And so, you know, 1 mole is fine. 1 mole. Okay. So that means each vanadium, each mole of vanadium has taken 1 mole of electrons. All right. So 1 mole of vanadium has gained 1 mole of electrons. So therefore, if the oxidation state of vanadium was original oxidation state was 5 plus 5, the new one, because it's each one of them is gained in electrons, so the new one, so remember plus 5. Now don't make the mistake of saying, oh, plus 5 is taking an electron, therefore it's become plus 6. No, electron neutralize the oxidation state, right? So it reduces it. If it takes an electron, it reduces it from plus 5 to plus 4. Original state equals plus 5, and therefore vanadium oxidation state, final oxidation state equals plus 4. Okay, so going over this issue, this question, the common mistakes that students, I mean, first of all, this question is a bit of, as I say, curveball, yeah? I mean, you expect it to be quite simple, and then suddenly they're talking about oxidation states, and that just throws you. What do you do? But if you don't know what to do, look, do the calculation that you can given the information, right? Whatever the information is given, just do whatever you can. Do the calculation. So we did this, yeah? We immediately did this, and that would have been 2 marks, even if you hadn't actually done any of the rest, yeah? It's not good enough because we want A stars, right? But it's still 2 marks if you're completely stuck. And then, of course, what they would have done is the marks would have been definitely for that would have been a mark. And then lost 2 electrons. Remember, reasoning gives you marks in this question because it's an extended response. So lost 2 electrons each. So I would have put that in proper English. Yeah, each mole of sulfur would lose 2 electrons. Okay, and then the last 2 marks would have been, well, one is definitely for the actual final, showing the final oxidation state, and then of course per mole. Yeah, so you know you would have. So 1 mark would have been here, you know, to show the plus 4, and then whether you get the mark here for plus 5, the original vanadium oxidation state, or you get it over there where you worked it out, yeah, you would have got a mark. So that's 6 marks. Okay, so another extended response question. Where students go wrong, obviously, is, as I say to you, I've seen many of these PV equals NRT questions where students don't remember what units are used. Yeah, for the pressure, for the volume. Okay, they make mistakes in terms of converting from one unit to another. As I said earlier, temperature, etc. is kelvins. Okay, and I think that's it. Okay, well, I hope that's been a little bit useful. I'm sorry about missing out a few things, you know, while I was speaking. But anyway, any other questions? Let me know in the comments. By the way, if you don't like my setup, the way you can see the questions being done, please let me know. Yeah, and I'll try and change it. I always try and improve it. Yeah, I don't want to keep doing the same thing, same way, if people are sort of not happy with it. Okay, the way I've got this set up. So I can change the setup if you want me to. Okay, thank you very much. I'll see you next Tuesday. Bye.